Hi, my name is Vishal Bakshi, and I'm one of the organizers of the PyDataPDX meetup. In this video, I'm going to walk through the Pandas 101 Lunch and Learn that Allison Slider and I hosted on March 4th. If you would like to join our Slack, please send us a DM on Twitter at PyDataPDX. You can find us on LinkedIn and meetup.com as well. All links are in the video description below. You should expect to achieve the following outcomes by the end of this video. Download and install Anaconda, set up a new project folder and environment using the command line, and explore pandas and numpy using JupyterLab. You can find Lunch and Learn materials in the PyDataPDX Lunch and Learn GitHub repo. You can also access the repo as a binder, which will open Jupyter Lab in the browser. To follow this video, you will need to download and install conda, which is a package manager that allows you to install different versions of Python libraries. Conda comes as part of the Anaconda distribution. You can download Anaconda at docs.anaconda.com/anaconda/install, where once you select your operating system, follow the instructions to install it on your computer. Once you have Anaconda installed, you should be able to access Conda from your shell. I'm using a Mac OS, so I open a terminal window, type conda-v, hit return, and see that I have version 4.10.1 installed. Over time, newer versions of Conda will be released. To update Conda, you run conda update conda, which will at some point prompt you to enter Y for yes to proceed with package installations. Once that's done, run conda update conda-build. This whole process will take about 5 to 10 minutes. Next, let's create a new project folder. From my home directory, I go to my documents/PyDataPDX folder using the change directory command cd. Then, to make a new folder, I type make directory pandas 101. I then cd into my new folder by typing cd pandas 101. I am using quotation marks because I have a space in my folder name. Type ls and hit return to see the contents of the current folder. Next, I'll create an environment within which I will do my work. An environment is a computer system in which code is executed with repeatability. Your Python script will depend on specific versions of different software packages, so you want to make sure you have those versions installed so that your script can run and produce expected results. I will create an environment called pandas 101 with Python and the packages pandas, numpy, and ipykernel using the following command: conda create _name pandas 101 python equals 3.9 pandas equals 1.2.4 numpy equals 1.20.1 ipykernel equals 5.3.4. Pandas is a data analysis open source software. NumPy is a Python library which supports multidimensional arrays and matrices. And ipykernel is the Python execution backend for Jupyter. After you hit return, at some point you will be prompted to type Y for yes to proceed with package installations. I already created this environment, so I will not create it again here. I activate my pandas 101 environment with the command conda activate pandas 101. You will see pandas 101 in the parentheses at the beginning of your command line prompt. I deactivate the environment with the command conda deactivate. You will return to your base environment. Again, you can see that in parentheses at the start of your command line. I can delete an environment with the command conda env remove _name pandas 101. Finally, I can list all conda environments with the command conda env list. Now that I have my environment created with the packages I want to use, I can start coding. I will use Jupyter Lab, which is a web-based interface for Project Jupyter. Jupyter is a project and community that develops open source software for interactive computing across dozens of programming languages. Jupyter Lab is automatically installed with Anaconda. However, in order to connect it with our conda environments, run the command conda install nb_conda_kernels. Now I can open Jupyter Lab. Make sure that you are in your base environment. From your base environment, run the command Jupyter Lab, that's two separate words, hit return, and a new browser will open with the Jupyter Lab interface. On the left-hand side, you will see the file browser, which will be showing the current working directory. In my case, that's the pandas 101 folder. In the Launcher tab, under the notebook title, I can see my conda environments. You click on the pandas 101 environment to create a new notebook using that environment. I'm going to open a notebook I've already prepared. On the top right corner, I see that this notebook is running in my pandas 101 environment. Double click or select and hit enter to edit the first cell. Set the first cell as markdown and enter a title. Hit Control Return to run the current cell, or Shift Return to run the current cell and either create a new cell below it if there is none, or select the cell below it. If a cell is being edited, hit Escape to get out of edit mode. You can then use keyboard shortcuts. For example, I can type A to create a cell above the current cell, or B to create one below. Hit DD to delete the selected cell. I'll start by importing numpy as np and pandas as pd. We'll start our exploration by creating a pandas.Series object. A series object is a one-dimensional array with axis labels. I can pass a scalar, such as a float, to the series constructor. I can also pass a list to the series constructor. I can create a series object from a numpy.ndarray, which is an array object representing a multidimensional homogeneous array of fixed size items. I can create a series object using a dictionary with keys as the index and values as the elements of the series. I can access the value at a particular index by passing the name of that index to the series object between square brackets. The value PyDataPDX is assigned to the index name. In general, a series object can be constructed using data that is of array-like, iterable, dictionary, or scalar value. Next, we'll construct a data frame which is two-dimensional, size mutable, and potentially heterogeneous tabular data. Here, I'll construct a data frame using a list of series objects. Each series object is created using a dictionary with the same keys, which become the index of the data frame columns. The names of the series objects become the index for the data frame rows. The data frame property capital T is an accessor to the method transpose, which will reflect the data frame over its main diagonal and write columns as rows and rows as columns. I can construct a similar data frame using a dictionary of dictionaries, where the keys of the final dictionary become the column index. Access a column by passing a column name to the data frame in between square brackets. If I pass a row name, I will get a key error, meaning none of the columns have this name. Only the columns can be accessed this way. To access rows, use the .loc method and pass a row name. You can also access the rows using the .iloc method and pass it a row integer location. So here, I'm accessing the 0th row, or row A. To access all rows in the two columns order and vowel, pass a colon as the row index and a list with the column names to the loc method. To access only rows B and C for columns order and example of fruit, I pass B colon C as the row index and a list of the column names as the column index to the loc method. You can also get rows by passing a Boolean array to the data frame in between square brackets. It will return rows with the index corresponding to the index of true values in the Boolean array. Here, the 0th element is true, and elements at index 1 and 2 are false. So I get in return a new data frame with only the first row. The vowel column is of Boolean type, indicated by the question mark. So if I pass that to the data frame, it will return a new data frame with the rows where the vowel column value is true. Use the tilde, which is the logical not operator, to return a new data frame where the vowel column value is false. You can also use the method logical_not from the numpy package to achieve the same result. Next, I'll go through some fundamental use cases for ND arrays. An ND array, which is a multi-dimensional or n-dimensional array, can be constructed using a single integer, array-like object, or list. I'll create a nested list A, where the first item is a list of integers 1, 2, and 3, and the second item is a list of integers 4, 5, and 6. I pass A to np.array, and it returns a nd array that I assign to a variable. The shape attribute of a nd array returns a tuple with the number of rows and columns. The first number in the shape is for axis equals 0, and the second number is for axis equals 1. Along axis equals 0, I have 2 rows. Along axis equals 1, I have 3 columns. I can use the max method to get the maximum value from the array. By default, it returns the maximum of the flattened array, meaning as if all values were in one row. If I specify axis equals 0, it will compare the values along axis equals 0 for each column to determine the maximum. In the first column, comparing 1 in the first row and 4 in the second row, the maximum is 4. In the second column, comparing 2 in the first row and 5 in the second, the maximum is 5. In the third column, compare 3 in the first row and 6 in the second, the maximum is 6. If I specify axis equals 1, it will compare the values along axis equals 1 for each row to determine the maximum. In the first row, along axis equals 1, the maximum is 3. In the second row, along axis equals 1, the maximum is 6. The min method to get the minimum value works in a similar way. The overall minimum is 1. The minima along axis equals 0 are 1, 2, and 3. And the minima along axis equals 1 are 1 and 4. The method mean will calculate the average of the flattened array by default. I can also specify the axis. The mean values along axis equals 0 are 2.5, 3.5, and 4.5. The mean value along axis equals 1 is 2 and 5. When you perform calculations between an array and a scalar, the scalar is broadcasted to each element of the array. I multiply the array and B, and the result is that B gets broadcasted to fit the size of the array so that the element-wise multiplication can take place. Broadcasting is when a scalar or smaller array is stretched in this way to match the size of the larger array, after which an element-wise operation can take place. I'll set the array back to the previous value. If I raise the array to the power of 2, 2 is broadcasted to each element, and each element is squared. Broadcasting between two arrays only works if they have either equal trailing axes or one of the trailing axes is 1. Trailing axes means counting the axes from the end of the shape. I'll create a new array that is 2 rows by 2 columns. The first array is 2 rows by 3 columns. Next, I'll try to add our original 2 by 3 array to the 2 by 2 array. The first trailing axis of the first array has a value of 3. And the first trailing axis of the second array has a value of 2. These are not equal, nor is one of them 1, so an error will be thrown. I'll now define a new array with a 1 by 3 shape. This shape is compatible with our 2 by 3. The last dimension is equal, and the first dimension is 1. The smaller array is broadcasted across both rows of the larger array, and element-wise addition can take place. Sometimes you need to create an array with a predetermined shape, which you will update later on with other values. The zeros method creates a ND array of a given shape filled with zeros. The shape of the ND array is given as a tuple. np.zeros also takes a keyword argument dtype, which specifies the data type for the 0 value. In this example, the array is filled with the 0-like Boolean value of false. The ones method achieves a similar result with values equal to 1. So that brings us to the end of this Lunch and Learn video. To go into more detail, please check out the official documentation for pandas and numpy. All of the links mentioned in this video are located in the video description below. There will also be a video for our Pandas 102 and Pandas 103 Lunch and Learns, and maybe even more if we continue to go on with this series. Thanks for watching.